Another extremely important example of uniform circular motion, or at least a motion that might be approximately uniform circular motion, is looking at an object in orbit around another object. Now, these don't have to have a uniform speed. They can have a varying speed, but sometimes we'll get something that is just about going around in a circle with almost a uniform speed. So let's make an approximation that we've got an object going around in an orbit around, say, the Earth. Let's say we've got a satellite in orbit around the Earth, and let's figure out some of the properties of this. Well, first of all, if the satellite is moving in a circle, there must be a centripetal force acting on it, a force towards the center of the motion. What force is acting as the centripetal force? In other words, what force is acting on the object toward the center of the motion? Well, it's gravity. It's the gravitational force, the gravitational attraction of the Earth and the satellite toward each other. The Earth attracts the satellite directly towards the Earth throughout the motion, which is always towards the center, so it is a centripetal force. But likewise, the satellite is going to be pulling on the Earth as well. But because the Earth is so much more massive, it's not going to move very much. It's not going to accelerate as much as the satellite. Remember, the accelerations will be inversely proportional to the masses, and if the Earth is much more massive than the satellite, it will accelerate much less than the satellite. Just as an aside, there are some interesting situations, like if you look at the motion of the Earth as the moon goes around, the Earth actually does wobble around a little bit like this. It does accelerate in a smaller circle than the Earth does, because of the attraction of the moon. Okay, well, let's see if we can figure out some properties of this orbit. Let's imagine that the satellite has a mass of m sub s, and the Earth, we'll assume, has a mass of m sub Earth, and I'm going to use a little astronomical symbol, a circle with a plus sign in it to represent the Earth. That's a little symbol that's used to represent the Earth for many years. The force of attraction, then, the centripetal force, is going to be, the gravitational force. The gravitational attraction between the mass and the satellite. And what is that? Well, it is big G times m1, we'll call that mass Earth, times m2, mass satellite, over the distance between them. Let's imagine that this orbit has a radius of capital R, so over r squared. If that is the force acting on the mass because of gravity, that must be our centripetal force, which is m. Well, what mass is actually in the orbit? It's the satellite, so ms v squared over the radius, which again is the radius r. There we go. So let's see if we can solve for v squared. What do we get? We get v squared equals, multiply by r, and we have one factor of r in the denominator. Divide off the mass of the satellite, and we end up with g mass Earth. V will then be the square root of that. So we'll take the square root, and there we go. That is the velocity of the satellite, the velocity, or I should say the speed, the magnitude of the velocity, that it must have in order to maintain uniform circular motion, in other words, for it to go around in a circle at a constant speed. There is a particular kind of orbit, particularly if we're really talking about a satellite like a communication satellite, where we can arrange the orbit so that the period of the orbit is 1 day, or let's say approximately 1 day. In other words, the satellite will go around the Earth in the same amount of time that it takes the Earth to rotate, approximately 1 day. We'll just call it a day. And what does that mean? In that case, the satellite will stay in the same position in the sky. Let's assume that it's going around the equator, going around in the sky above the equator. It will stay in the same position in the sky as the Earth rotates the satellite will go around the Earth with the same period, and so it will always maintain the same position in the sky, which is good for communication satellites, things like that. So let's see if we can figure out at what radius would this have to occur. What would the radius of the satellite be? Well, a period of 1 day, we convert that to seconds. We get 24 hours per day, 3,600 seconds per hour. That gives us a period of 8.64 times 10 to the 4th seconds. Now, what do we want? We want the period to be, remember, what's the period in terms of the radius of the velocity? Well, the period would be 2 pi v over r, oops, got that backwards, 2 pi r over v, 2 pi r over v, which is what? So this will be 2 pi capital R divided by v, so we'll flip this around, so this will be square root of r over g m Earth. There we go. So let's see if we can solve this for the radius. We'll square the whole thing, and what do we get? We get t squared equals 4 pi squared r squared, and then we square this, we get r, another r, so that's r cubed over g squared mass of the Earth. Solve this for r, take the cube root, and what do we get? We get r, well, I'll just leave it in terms of r cubed. R cubed is equal to, oh, I'm sorry, we square this, we don't end up squaring the denominator. That was silly. So we square that, we don't end up squaring the g and the mass of the Earth, right? Solving for r, we'll get r cubed equals g mt squared over 4 pi squared r cubed. We're leaving the r cubed there. 4 pi squared. There we go. There's r cubed. Putting in g, the mass of the Earth, so what do we get? G, 6.67 times 10 to the minus 11 newton meter squared per kilogram squared, times t, the 8.64 times 10 to the 4th seconds, kind of running out of room over there, squared, over, oops, I forgot the mass of the Earth there. Mass of the Earth, which is 5.98 times 10 to the 24th kilograms, and then divided by 4 pi squared, and what do we end up with? R is equal to 4.23 times 10 to the 7th meters. There we go. If we could arrange a satellite to have a radial distance, remember that would be from the center of the orbit, in other words from the center of the Earth, of 4.23 times 10 to the 6th meters, we would end up with what is called a geosynchronous orbit. A geosynchronous orbit. In other words, it's synchronized with the rotation of the Earth. If we subtract off the radius of the Earth, we would find the distance from the surface of the Earth to the satellite, and that turns out to be 3.59 times 10 to the 7th meters, or about 36,000 kilometers. So if we have a satellite about 36,000 kilometers above the surface of the Earth, we end up with this geosynchronous orbit. Okay, very, very good. Let's take a look at some other kinds of rotational motion. Rather than basically a particle going around in a circle, let's go back to what we had talked about before. Imagine we have a solid object that is rotating around like that. Let's generalize our rotational motion to something that's rather than just a point mass, but a solid object that is rotating. Let's imagine that we are looking at some object that is rotating, so not just a point mass going around uniform circular motion, but some extended object that is rotating around like this. Well, first, let's imagine that we can identify the axis of rotation. So this wheel, as it's rotating around, is rotating around this axis. Every point on the wheel is then going around in a circle around this axis here. So let's assume that our axis is stationary. It's held fixed. We certainly could have something more complicated where we have an object that's rotating and the axis is moving as well, but for the time being, let's assume that our axis is stationary. We don't have to imagine that it is circular. So we could have some extended object, but let's imagine that the axis of rotation is held fixed. So the object is rotating around the axis of rotation, whatever the shape is. So how are we going to describe this motion? Well, before we start talking about motion, how will we describe, let's say, the orientation of the object? Rather than here, is it here or down here or something like that? How will we describe that? Well, let's imagine that somewhere on our object we put some point, or we consider some point on our object. I've got a little dot here. So that's going to be, that will allow us to identify the orientation. The dot over here is different than having the dot over here. With a wheel it doesn't look any different, but if we had some irregularly shaped object with some point attached to the object, when this rotated around, that point would move around. This point we will call our reference point. Okay? So, as our object moves, the reference point rotates around. But we're assuming the axis of rotation stays fixed. From the axis, through the reference point, let's draw a line. We'll call this our reference line. So, as the object rotates around, our reference line will then rotate around with the object. Okay, it doesn't always have to spin in one direction. It could, maybe our object will turn one way and then turn the other and then back and forth, or however it wants, some random general motion. So our reference line will move around. How are we going to define where our reference line is? Let me say not define, how will we describe it? In addition to our reference line, let's define an axis. Not an axis of rotation, but an axis like the x-axis. We are going to define a fixed axis like the x-axis. So this is a fixed axis. And when I say fixed, what I mean is fixed in space, fixed relative to us that's observing it, or something like that. If we were going to talk about, say, this wheel moving around, we might define then an x-axis like this, pointing in the x direction, so as the wheel turned, the x-axis remains stationary. The reference line rotates around, but the axis, the fixed axis, stays where it is. We will then define the position of our object by stating what is the angle between our fixed axis and the reference line. So we'll use theta to tell us where the object is, what's its orientation. This we will refer to as the angular position. Remember when we were talking about one-dimensional motion and we talked about, say, an x, the x value told us the position in one-dimensional motion. Well, when something is rotating, we'll talk about the angular position, theta. And as the object moves, theta can change. Theta might be a function of time, for example. Theta might be a function of t, like we might have had x as a function of t if the object were moving along the x-axis back and forth, something like that. Okay, there we go. There's the angular position. Now, what if this is changing and moving? We can describe how rapidly it's moving. Is the angle theta, is it changing slowly like this? Or is it changing rapidly like this? Well, we'll define how rapidly the object is rotating around. Actually, but before we do that, let me mention one more thing before we go any further. What are the units of theta? What units will we use? Well, typically, so far, when we have been talking about angles, like angle of incline or the angle of an initial velocity or something, we've always been talking about things in degrees. Well, when we're talking about the rotation of an object, we're going to use a new angular measurement. And those are radians. And we'll write radian, R-A-D for short. So these will be the new units that we will use for angular measurement. Well, what's the conversion between radians and degrees? Well, what we have is that 2 pi radians make one complete circle. In other words, 360 degrees. So 1 radian is equal to 360 degrees divided by 2 pi. Well, that turns out to be about 57.3 degrees. So let's just think about that. What kind of an angle are we talking about? I've got a big protractor here. So there's 0, 10, 20, 30, 40, 50, 55, 57, somewhere around there. So something like that. That is about 57.3 degrees approximately. So that is 1 radian. It doesn't look like any special kind of angle. It doesn't look like a right angle or a 45-degree angle or anything like that. But it's about a 57.3 degree angle, and we're going to call that 1 radian. The reason that we use radians is because it makes the mathematics much, much easier later on. We'll be talking about specific angles in our equations rather than just sines and cosines. And when we talk about specific angles and multiply and things like that with them, it makes it much, much easier. The mathematics is much, much easier if we measure them in radians as opposed to degrees or even something else like gradians or something like that. So we will measure our angles in radians. Even though we will be using radians, at no time will we be taking trigonometric functions of angles in radians. So if you have a calculator set in degrees, leave it in degrees. Even when we're going to be talking about radians, we're not going to be taking any trigonometric functions of the angles in radians. So keep your calculator in degrees. If you start moving it back and forth, most likely you'll end up forgetting to change it back to what you want, and that can lead to mistakes later on. So let's leave our calculators in degrees. All right, great. So back to theta. If theta is changing, if our object is rotating around, we can define the rate of change of the angular position, and we'll call that the angular velocity.